positron beam. It's going around more or less in a circle, so it's the age of accelerator physics was born after the end of the Second World War, and there's several billion electron volts. We call them giga electron volts now. The Large Hadron Collider is up to tera electron volts, but you need several billion electron volts. You smash the protons in this beam into a target, and then you do some little analysis on them, magnets here and various things, and you bend them round. So you can tell by the late arrival of these negatively charged particles, these other negatively charged particles which were known at the time to exist, they arrived before a millimicrosecond is a nanosecond in today's terminology. These later arriving particles, identify them as a particle with the same mass as the proton. So you needed a beamline to isolate the antiprotons and to kick them out into the detection chamber. We use something similar nowadays, except we don't kick them out into a detection chamber. We kick them out into an experiment which collects them. I'll show you. So when antiprotons annihilate, they're a composite object like protons. They have inside them something called quarks or antiquarks, and when they annihilate, you get a slew of other particles given off. So at this point here, this is an antiproton annihilating, and if you look, and this is a beautiful old now bubble chamber photograph, you'll see that there are various things coming out from this point. There are actually 5 of them, and these are charged particles which come off when an antiproton annihilates. It can annihilate with a proton or a neutron. It just takes it out, and basically these charged particles can come out, several of them. We call them pions, for want of anything better, and they leave a visible track behind them in this bubble chamber, so you can detect the point at which the antiproton annihilated. We do that in our experiments using somewhat more advanced technology, but this is important. When an antiproton annihilates, it gives off a slew of particles, charged particles, which leave a mess behind them when they travel through matter. Okay, and we can detect that mess. Getting back to positrons, what about positron annihilation? Well, this is a curious thing indeed. When positrons are emitted from radioactive sources, the probability of them actually hitting an electron and annihilating is very small. So when a positron is emitted, there are positrons in this room right now coming from cosmic ray muons and stopping. Some of them will be stopping inside you and I as I speak. When they stop, they actually slow right down to thermal energies before they annihilate. Okay? And that's important. So they reach what we call thermal equilibrium with the medium because the annihilation probability is much smaller than those for losing energy. And when they annihilate, it's a very characteristic signal. You get this pair of gamma rays. So it's really E equals mc squared. You've got twice the mass. The positron annihilates with an electron. 2mc squared comes out. And the most probable thing for it to happen is it comes out of a pair of gamma rays back to back. Okay? And that's because the positron is slowed right down. There's no excess energy. It's lost all its energy. So the only energy coming out is the rest mass energy of the electron and the positron. So you get this pair of back-to-back gamma rays close to 511 keV. I won't go into why they're not quite 511 keV, but it's a very characteristic signal indeed. So what can this be used for? Well, recall earlier on I said that you can make common atoms and insert these into molecules, for instance glucose or water or other things. You can make them radioactive. You inject them inside a patient, and this radioactive, say it's glucose for instance, and the glucose goes to the parts of the body which are working, and if you're alive then the body will be working and the glucose will go, and say it will go into your brain, and the glucose will go to where the brain is working the hardest at that particular moment in time. And my brain's working pretty hard at the moment, maybe yours is as well. I'm speaking, so a part of my brain is working. Hopefully you're listening, and actually a slightly different part of your brain will be working to mine. Okay? So the glucose will go around, and it will find where the activity is, and the positrons will preferentially annihilate there because they're tagged to the glucose. So here is a picture of a normal brain. This, if you like, is if you cut the top of my head off and then cut another slice and lay it up like that, that's what you're looking at. You're looking at a slice through a brain, right? And you can clearly see the difference between the glucose uptake in a normal brain, 2 slices, and the equivalent slices in someone who's suffering from pretty awful disease. And these can be seen ages before the other distressing symptoms of these diseases can be found. And even ordinary everyday things, I don't know what working means, but this is slices through the brain when someone's looking. So you see your brain's working very hard behind your eyes. Listening, lo and behold, something behind your ears is working. Thinking, hopefully you're doing that as well. So something back there is working. Remembering, working. Remarkable pictures of the brain at work, taken using antimatter. Pictures using positron emission tomography, PET. And that's my brain. I hope it's a false color image. I volunteered for a study. Before going to Swansea, I was in London and I volunteered for a study since I've been working with positrons all my life, I thought I might as well have some on the inside. So I went to Hammersmith Hospital in London and they stuck me in a machine and injected me with a labeled drug called benzodiazepine, which is used in the treatment of epilepsy. So the purple bits, apparently, they tell me, are where that drug has been taken up. So that was my brain in 1998. It's probably a bit smaller than I now. So I want to go back to the physics now and ask a question, a big question. Is there any antimatter out there in the universe? Remember I said when positrons and electrons are created, they have to be created in equal amounts, and that holds for antimatter and matter. Whenever you create anything from pure energy, you have to make exactly the same number of pluses and minuses, to put it simply. So is there any antimatter out there in the universe? Well, remarkably, there is. Positrons come from radioactivity, and there is a lot of radioactive material out there in the universe. We're sitting next to a nuclear reactor. That's the sun. That's a very nice thing to be near. Most of the universe is not like us. We've got a star next to us radiating heat. This is a solar flare from 2002. Many kilograms of positrons were created during that solar flare. A positron weighs 10 to the minus 30 kilograms. So many kilograms weight. This is a photograph of this 511 keV radiation taken using a gamma ray telescope coming from the center of our galaxy. There is a positron source in the center of our galaxy emitting 10 to the power 43 positrons per second. It's probably a black hole which is intensely radioactive because of the material being put into it. You do not want to be anywhere near the center. This is only our galaxy, okay? Nothing fancy, we live in it. But there's a black hole at the center of it emitting positrons so there are positrons out there. But if you look back at the Big Bang, here we are out here, this is where we live, this is the part of the universe we live in where there are atoms and molecules around. The universe is very quiet, actually. It's mostly full of nothing. It's just full of 2.7 Kelvin radiation and nothing else. We just happen to live near a star. And so we live, otherwise we wouldn't. But as the universe was cooling down from the Big Bang in the first few fractions of a second, a couple of things happened. The antiquarks disappeared, and a short time later the positrons disappeared, and we don't know why. So by the time the universe cooled enough to about 10,000 degrees so that you could start to make atoms, only hydrogen was formed, and no antihydrogen was formed, and we don't know why. So there's an experiment sitting up, I'll show you a picture of it. This is the alpha magnetic spectrometer. This is a particle detector. This is it sitting at CERN being tested before it was sent to NASA. It's sitting up there. That's a picture of it on the space station. It's looking for primary cosmic rays which come and when they hit the atmosphere, they create all these particles, which makes it complicated. So it's sitting above the Earth's atmosphere looking at these primary cosmic rays coming down to try and see if there are any antimatter, any antinuclei in those cosmic rays, because if there were, that would tell us that there were anti-galaxies out there. But every single time we look, and including so far on this experiment, because they have the first data back, no, there is no antimatter out there. It seems that it all disappeared. So when the universe was born, somewhere along the line, the positrons and the antiquarks disappeared. And what was left over, about 1 part in a billion, is what the material universe is made of, what you and I are made from. We're made from the matter that somehow survived the Big Bang. And we don't know why it survived. So can we make the atom on Earth that the universe didn't get a chance to make, namely antihydrogen atoms containing the antiproton and the positron? And to do that, because we need accelerators, I have to come to CERN. I didn't start my career here, nothing like it. I started in a very small lab about a fraction the size of this room in London working with positrons, but we have to come, we need the antiprotons, so we have to go to an accelerator. We're a very small part of it. I hope you'll get a chance to see this wonderful machine. It's a special one because CERN is normally associated with acceleration, but we work at the antiproton decelerator. So this machine is a fantastic piece of technology. It actually captures antiprotons created at a target and slows them down. That's what it looks like. It's located here. It's a ring machine. If you get the chance, go and see it. You get a bunch of protons in. You make the antiprotons. You capture them in this ring. There's a vacuum chamber inside here. I won't go into the details, but by every 100 seconds, it emits these antiparticles into the various machines. It slows them down to a relatively low energy. What we do then in these machines is that's a photograph of the machine, so that's our machine. So this is sitting inside the antiproton decelerator, and that's where we capture the antiprotons, and this is where we make our positrons. The radioactive source is down this side. So in order to capture these particles, they're charged particles, and what happens to a charged particle is that it's easy to hold in a way because it's got an electrical charge and it will respond to electric and magnetic fields. So if you apply a strong magnetic field along the axis here, the particles will perform corkscrew trajectories. So the strong magnetic field running along the axis of these tubes here, did I put it in my pocket? Yeah, I did, actually. What a clever chap. They look like that. These are electrodes. So those are electrodes along the axis of a magnetic field. The particles, the antiprotons and positrons, will perform a corkscrew trajectory. We then apply voltages to these caps. We know when the antiprotons are coming, and by applying various voltages to these these electrodes, these cans, we can capture them and make them bounce backwards and forwards. So that's what it looks like. There's a set of electrodes there, a photograph of an early set that we were using. The antiprotons arrive, they pass through a foil, they get bounced off an electrical potential here. Before they come back, we know when they're coming in a pulse. We can ram on, close the door here, putting a 5 kilovolt potential on, and they bounce backwards and forwards. Before they arrive, we put a little electron cloud inside there. Electrons are marvelous in strong magnetic fields. They go around in circles like completely crazy, and they radiate away their energy. It's the same way your phones work. You make an oscillator like this, and it radiates. It's electromagnetism for you, but an electron will do it in a strong magnetic field, and they will sit cold in there. When the antiprotons arrive, they pass to and fro in this electron cloud. They bang into the electrons, and they excite the electrons, but the electrons themselves radiate the energy away because they're in the strong field. So it's like a refrigerator. The electrons are a refrigerator for the antiprotons, and they slow down, and eventually they sit on top of them, and we then kick the electrons out. So we get cold antiprotons in a volume about the size of the end of my thumb. And we cool them down to temperatures. So the LHC is up here. This is a logarithmic scale. We tried to cool them down to milli-electron volts. The LHC is at several tera-electron volts, but we want to work at the opposite end of the scale. Okay, so just to remind you, if we put positrons and antiprotons together and make antihydrogen, then those charged particle traps are not going to work for the atom because it's electrically neutral. So it will fly off, hit the wall, the antiproton will annihilate, and the positron will annihilate, and we'll get those two things together in a coincidence at the same time. And that's what that event is there. That's the antiprotons annihilating, four pions coming out, and there's the back-to-back gamma rays. So that's antihydrogen detected in the lab just over the road at CERN in 2002 for the first time. But what we're doing now is we actually want to trap the antihydrogen and hold on to it to do some experiments. And you might think, well, how do you hold an atom? Well, an atom has something called a magnetic moment. Basically, the electrons in atoms are like they're little electrical currents. You can view them as moving around the nucleus. And so they make a little magnetic field, and you can interact with that magnetic field using magnetic fields. And anti-atoms are just the same. It's a property called the magnetic moment, and it's weak. It's not very strong, but if you make a three-dimensional magnetic field minimum, you can trap the atoms. Now, this is a complicated diagram. There's so much physics in this, I don't have the time to explain it. But some atoms, if you know yourself what magnets are like. If you put a north pole next to a south pole, the bar magnet, and if you try and put two north poles together, you have to work like crazy to put the north poles together. So if the atom's magnetic moment is pointing in the wrong direction in the field, it will have to do work. It will lose kinetic energy, and it will be transferred to internal energy. This is the internal energy of the atom in the magnetic field. Conversely, those that have their magnetic moment in the right direction will gain kinetic energy. So these atoms here will not like to go to a magnetic field, and if they've got a low enough kinetic energy, they will slow down and stop and bounce back, and they'll be captured. Those will annihilate. If we can flip them from that state to that state, then if we make one jump from that state to that state, it will immediately go to the wall and annihilate. Okay? So that's our apparatus, the alpha apparatus. I won't go into the details of it. I've got a little video to show you, but we have a magnetic minimum made by these cores. There's a superconducting wire with hundreds of amps going through it, an annihilation detector. These are the electrodes here. That's what it looks like. So this is Dan Brown's vial of antihydrogen. It looks monstrous like that, and these are the bus bars coming in carrying hundreds of amps of current. This is the apparatus as it was. This is a good, when it's frozen up like this, it means it's working. If I turned up and it wasn't looking like this, it means it wouldn't be working. The antihydrogen is made inside there, and the detector's all inside that large can. So let's cross my fingers that. Okay, so a company made a little video for us about the experiment, the antihydrogen experiment. So here it comes. We're going to peel away and go through into the innards of the experiment. You can see the annihilation detector on the outside. It's layers of silicon. It's just like the detectors that are used in the LHC, except it's very simple. It's very small. I could hold it in my hand like this. These are the coils which make the magnetic field minimum. We call them mirror coils, and an octopole with this serpentine winding, and they get powered up like this, so the current goes round like that, and it makes a three-dimensional magnetic field minimum in the center of this thing. Next, we're going to see, so that's actually wound, that's the vacuum chamber. It's wound on the outside of the vacuum chamber, and right on the inside, as close as we can get it to the magnetic fields. These are the electrodes that hold the charged particles. Okay, so these are these things. This is a stack of them put together we apply various potentials to them. So there's the electrical potential. The positrons, we get them to sit there. The antiprotons, we do something really cool to them. They're little clocks sitting in their little well, and we just give them a little tickle and make them bounce a little harder in their well. And out they come in a little burst, and like that. And they disappear inside the positron cloud. And with a very, very, very high probability, the following thing happens. The positrons come along, two of them hit each other in the vicinity of the antiproton. One of them gets captured and the other one disappears off to conserve energy and momentum, and we make antihydrogen. The next thing we do is, as I said, we want to trap it. So we make this magnetic field minimum. Forget what this bias potential is, that's a technicality. But the antiatom is sitting in the magnetic field minimum there. It's trapped, it can't hit the electrodes. The first experiments we did was then just to drop this magnetic field quickly, and out it went. That's how we detected that we had trapped antihydrogen. And then when it hits the outside, you get this pion signal, and we detect the tracks, reconstruct them so we can figure out where our antihydrogen annihilated. What we've done very recently is we've actually done some spectroscopy on it. We've been able to tickle, there's the magnetic moment, it's pointing against the magnetic field. Here it comes, we apply some microwaves, we flip the spin, and it becomes untrapped, and it disappears. The microwaves come along, so this is the first time we've been able to get to microwave spectroscopy of any spectroscopy of antihydrogen, and we're going to be able to improve on this soon. So, what do I conclude? Antimatter exists, but there seems to be none of it out there in the universe. Incredibly, in medicine and in other areas, it's not just medicine where positrons are applied. We've found uses for it here on Earth, and it continues to be an object of fascination and inquiry for science. So watch this space for more, and thanks for turning up this morning. Thank you.